let's make a plot of the temperature variation along the wall and also along the center line. And this plot is very important to develop some fundamental insights into the heat transfer problem, and it's key to developing expert thinking in heat transfer. I've learned more from this simulation than from my heat transfer course, where there were no simulations. I think simulation is very good at making things concrete through the visualization and the interactivity and so on. I'll go to CFD Post, and I want to plot. I've gone into the 3D viewer, I've gone back to the temperature contours, and so let's plot the temperature along the wall first. What I need to do is I need to create what CFD Post calls a location, a line along the wall, and then extract the temperature along that line. So first let's create that line. So I'll say location, line, and I'll call it wall. Make sure you're editing wall. And we want to go from the inlet, so the axial location is 0, and the radial location is 0.06. So that's that point. And then this goes to 15, and that's 0.06. So that should be that point. And then we will say, hey, you know, give me 200 samples along that line. And I'll say apply, and it adds that object to this tree. I can turn it on or off. Now it's not over here because this is stretched, so I can turn off the temperature contours and turn on the wireframe. And by zooming in, I can make sure that that line is along the wall. And remember, everything's reflected, so that's why you're seeing two yellow lines. So I have the location. Now let me create the plot. So I'll say chart, and let me say axial temperature variation. And I'll go to the data series tab, and the location is the one that we just created, wall. And along the horizontal axis, we want to plot the axial distance, which in Fluent notation is x, and along the vertical axis, I want to plot the temperature. And I'll say apply. Okay, so as I'm going along the wall, it stays 300, and then as I'm adding the heating, it jumps instantaneously. And then it becomes linear. And an expert would look at this and say, hey, the temperature variation is becoming linear here, so the flow is becoming thermally fully developed. So that's what it's looking like. I'll get to more of that in just a little bit. This kink, I think, is a result of the fact that that corner is both a wall and the outlet. And the kink becomes smaller as you refine the mesh. And we can export this to Excel. So I'll say export, and I'll go up a couple of levels. I'll go to my working directory, and I will say twall. So I can say temp _ wall, give it a suitable name. And if you go in and look at that CSV file, you should see that you're getting all that data, which you will, if you want to calculate the Nusselt number, you will need, or the convection coefficient. Now let me add a second plot, the temperature variation along the center line. So if I go back to the 3D viewer, let me zoom in here. I want to create another line along the center line. So what I'll do is I'll highlight that, the first line I created, and I'll say duplicate. And I'll call this center line. And it doesn't like that because there's already center line. So if I cancel out of there, there's already center line here, but that comes in as a surface. So I will say duplicate. I'll do that again. Now I'll call it my center line. And I'll say OK. And then you have to double click on my center line to make sure you're editing my center line. I tend to forget to do that. And now instead of that line being at a radial distance of 0.06, it's at a radial distance of 0. Okay, apply. So now I have the line along the center line. So let me go back to my chart. And it's over here, axial temperature variation. So I've double clicked on that, and now under data series tab, I'll add a new curve. And for that new curve, the location is my center line. Okay, so so that shows you the variation along the center line, and you can see that the slopes are becoming the same. So this is T center line, this would be T wall, and you can also add in the mixed mean temperature, okay, which will be something like that. So that'll be Tm, and that's a hand calc. You can do that based on the energy conservation. So that's like the bulk temperature. And when the flow becomes thermally fully developed, this distance won't change, will be the same. So that distance will be the same as that if the flow becomes thermally fully developed. That's that's a definition of the thermal fully developed. And if you look at the definition of the convection coefficient, so I want to get the heat transfer at the wall, which is known. So you use H. And then you multiply it by the difference between the wall and the mixed mean. So that's that difference. Usually you use H to get that, right? But here, you know this is a boundary condition. So that's constant. And when the flow becomes thermally fully developed, that's constant. So that's constant. And we can calculate that. And then if you non-dimensionalize it, you'll get the Nusselt number. So you can see why the Nusselt number has to be constant right over there. You can also think about, how the slope is different for the center line and for the wall. The center line, hasn't felt the effect of the heating yet. So here, it's flat, whereas at the wall, the temperature increases instantaneously. So the slope is very different. You can make this plot very pretty. And I show you how to do that in the laminar pipe flow module under numerical results. If you go towards the end, you'll see you can make this all very pretty, by changing the font and so on and putting in a title. But you can do this plot in Excel, right? So you can export this, you can export that, and in fact, if you do export, you'll get both of these data lines, and then you can add in that and do this plot, all 3 lines in Excel.